Welcome to my new calculus channel. My name is John Gabriel. Today I'm going to continue off from the previous video where I talked to you about how to derive arc length, and obviously the next topic that fits in beautifully with arc length is the line integral, or the contour or path integral, and that is what I'm going to talk with you today. So let's begin. So my claim is that all integrals are line or contour or path integrals. Line, contour, or path all mean the same thing. Okay? Now, let's consider the line y of x is equal to 0, or the x-axis, because that is the line that we use to scale our integral. In other words, if we're looking at a particular area between a curve and the x-axis, we're scaling the integral according to the x-axis. Okay? In other words, the length of the x-axis. And why is that so? Well, because we have to calculate the arithmetic mean of all the y-ordinate lengths in that interval. There are infinitely many, but don't worry. The mean value theorem and the fact that that particular arithmetic mean is possible due to a telescoping sum allows us to do this. Okay? So, and we know from this particular equation that dy dx is 0 and dx to dx is 1, right? Because if we take this particular ratio and divide dx by dx is 1, and this particular ratio divided by dx is 0, right? In other words, dy divided by dx is 0. So now the symbol for a line integral is this, and we usually denote it by ds, which is the differential for the distance formula. And normally, when we don't write the little circle on the elongated s, then we write the name of the path along which the integration is taking place, which is y is equal to 0. And of course, this here is actually just equal to the definite integral, because although we write the definite integral like that, we actually mean this, okay? That's what it means. And I put the question mark in there because I'm about to show you that this is the same as this. So ds dx is actually equal to this, and this here you'll see later on is just a scaling factor, okay? And so dy dx is 0, so that gives us 0 for this and 1 for this, which means that the whole radical evaluates to 1, and so we end up having the line integral just along the x-axis equal to the integral of dx, which is the definite integral. So now, if we consider integrating along the line y of x is equal to x, then dy dx is 1, and of course dx is still 1, right? There is no difference with dx to dx, regardless of what the function is, or dy to dy. They're just equal to 1 if they're the same differential. And again, we want to see if that is equal to the square root of 2. Well, it is. Look, dy dx is 1, dx is 1, so it's the square root of 2 dx. So if we write it like that, you see, notice the previous one we wrote y is equal to 0, this one we write y is equal to x, and that's going to equal to the integral of root 2 dx, which is just root 2 integral dx. It should therefore be clear to you now that distance formula is used implicitly in every different integral. So while you don't see this process in the definite integral like that, it is there. You just don't see it, okay? It's happening. Otherwise, you're not integrating. You're not finding the area by taking the product of two arithmetic means, right? Okay, so then from the examples, we saw that if an arithmetic mean of all the y values is being calculated along the x-axis, then the scaling factor is simply 1, isn't it? If the arithmetic mean of all the y values is being calculated along the line y is equal to x, the scaling factor is a root of 2. And these facts are verified when we calculate the areas of each integral. So let's see a demonstration. All right, so this is the line y equals to 1, or f of x is equal to 1, and let's look at the areas. So we'll see that this area here is just 1, right? And if we move this anywhere else, it's always the area of this particular blue block here. This blue area plus this red area is root 2 times f of x equals to 1, right? So that means that this area here plus this area here is actually equal to the square root of 2. And that will also be the same as if we actually calculated the area under y is equal to root 2, which is this line over here. Yes, does that make sense? Yeah. So it doesn't matter if we move it along. We'll see that the scaled value is just simply this entire area here. The scaling integral will give us the entire area, which is under this line from this point to this point, whereas if we're just calculating without scaling, we'll just get 1.2, which is just this area. Make sense? Okay. Now let's look at the scaling. So if we've got that particular line there, okay, and we want to integrate along that line, it's the same as integrating when the line is on the x-axis. In other words, instead of integrating from here to here, we're integrating from here to here, right, to this point here. So obviously, if you're integrating along a longer path, you're going to get a bigger area. Yes? Does that make sense? Okay, very good. Let's look at one last example of scaling. So it doesn't matter whether the line is a straight line or a curved line, or if this is a curved path like that. Again, it's as if we're stretching this line out across the x-axis, and we're integrating from not this point to this point, but from this point to this point. Okay? So see, as we move that area, this area here, obviously we'll be seeing the effects of the scaling. Okay? Right? See that? Okay. Very good. So now, in the previous video, I explained to you how the arc length is easily derived in the new calculus. I also explained the new calculus integral and how it is determined in finite steps because of the mean value theorem. Do you recall the dynamic applet I showed you many years ago? This one here? You see that the area that is being calculated is done in finite steps. This is the new calculus definition of integral. And this mu p is simply the mean value for each of the partitions, okay? Not this main one, although this main line here symbolizes the mean value of all the ordinates, the y-ordinates in this area. I've only given you the value up to 4, but it doesn't matter because regardless of the value of k, the area is always the same. Watch down here. That's 8.704. Yes? Still 8.074. Okay, it doesn't matter what the k is. So you could go all the way up to infinity. So, presumably, if you could do that, it would be the same area. So there is no such thing as infinity, and we don't deal with infinity in the new calculus because it's a crap or junk concept. Right, so these videos, these applets and the video will be uploaded, and you can actually access them in your own time. So that's it for now. I think the best thing for you to do is to go off and study these things and verify that everything I've been telling you is true, which of course it is. Okay, so that's really all for now. Till next time, this is the New Calculus channel, and my name is John Gabriel. Goodbye.